We are being recorded. Let's get into our study. And did anybody have a problem accessing the first recording? Okay. All right. Let's see. Where is the link to share the screen? Unfortunately, I cannot find it. Oh, here it is. Okay. All right. Here we are. Can you all see the shared screen? All right. Okay. So last time we were looking at acid-base reactions between Bronsted and Lowry acid and base reaction. We learned, or rather we reviewed, that the Bronsted and Lowry acid-base reactions have their counterparts on the other side of the arrow, called the conjugate acid, conjugate base. Depending on who donates the proton, H plus, and who accepts that H plus, we have the conjugate acid and the conjugate base. And we learned there is a conjugate acid base pair. Here, HA and A minus on the other side are the pair. And the other pair would be this base here, and which is H2O and H3O plus. Usually we write the conjugate acid first, followed by the base. Now, um, let's see where we left off here. Yeah, Lewis acid and Lewis base. Lewis acid, Lewis base definition is different. A Lewis acid is a compound that accepts a pair of electron, And a base, a Lewis base is a compound that donates a pair of electrons. Here, trifluoroborane is accepting a pair of electrons from water. Just the fact that a bond is forming between them, where the bonding electrons are coming from one compound, both the bonding electrons, means that it's a Lewis acid Lewis base reaction. And there is no need for that to be a conjugate acid and a conjugate base on the other side, as you see here. Okay, thank you for letting me know, Sarina. And a few basics that we talked about when we ended our conversation on Monday was that in water, the pH and the pOH, when added together, should equal to 14, 1,4. When the pH is less than 7, it's an acidic solution. When the pH is greater than 7, it's a basic solution. Now, there is Henderson-Hasselbalch equation, the equilibrium constant equation. None of those things do you need to know in this course. Keep in mind simply that pH is pH plus pOH equals 14. And when we say pH plus pOH, we are talking about the conjugate acid base pair, the pH of the acid and the pOH of the conjugate base. Once that is in your mind, remember also pK, that if a solution is strong, if you have a strong acid, that means it has a large Ka value. That means it will have a small pK value. And similarly, if you have a weak acid, it will have a small Ka value. That means it will have a large pKa. The smaller the pK, the stronger the acid. The larger the pKa, the weaker the acid. Same with the base. The smaller the pKb, the stronger the base. The larger the pKb, the weaker the base. All right, so we looked at this reaction on Monday, and we saw how to find the direction the equilibrium lies, depending on the pKa values. The smaller the pK, the stronger the acid. So between this acid and this other acid, now when you look at this reaction, you will not be told in an exam or a homework that which is the acid. You know which is the acid by what happens. And the definition to go by is the Bronsted-Lowry definition. The Lewis acid definition, don't worry about it. You will not hear about it again in this chapter. It's all about Bronsted-Lowry. So here, the fact that this compound, acetic acid, as I happen to know it is, you know that it's an acid because it's losing or donating away the proton to OH minus. So this compound is the acid. Over here, water is donating its proton to this compound called acetate. So you know that's the acid. So between these two acids, which is the stronger acid, that's what's either given to you, like here, or you would be given structures and given a table in which you would find the values for these two, water as well as acetic acid. Once you know the values, you know which is the stronger acid and which is the weaker acid. That is all. That's all you need to know, which side, which direction the equilibrium favors. Does it favor turning more into the products, or which means it lies in the forward direction? Or does it favor turning more of the reaction constituents into the reactants, which means it lies on the reactant side, on the reverse side? But the fact is that the reaction will lie in the weaker side, whichever is the weaker end. That is how nature works, where everything moves towards more stability. Being a strong acid means being unstable. Being a strong acid means being highly reactive. Being a weak acid means not being highly reactive. So that makes sense why it should lie to the forward direction in this case. Because if this is a highly reactive acid, it will react. If this is a less reactive acid, that's where we will stay at. after turning the highly reactive acid onto the less reactive version. That's how the reaction always moves to the weaker side. Keep that in mind. Another thing to keep in mind is that the weaker sides are always together, which means the weaker acid, if it's here, the weaker base should also be this compound. Because remember, one is the acid, the other is the base on each side. If this is the acid, this is the base. If this is the acid, this is the base. So here, this is the base. This is the conjugate acid, this is the conjugate base, this is the regular acid, this is the regular base. Between these two, we can find out their pKb values as well. But if you don't have to, you don't need to find it. Then simply know the reaction. This will be a weaker base as well. Now, if I wanted to know the value, you helped me last time find out the value by using that equation we saw earlier, that pKa plus pKb here, pK of the acid and pKb of the base should equal to 14. So by that logic, if this is 4.75, this is the conjugate base. The pKb of this conjugate base is 9.25, right? Because 4.75 plus 9.25 equals 14. All right, so keep that in mind. This is 9.25. And what is the pKb of this? It was negative 1.7. 15.7 plus negative 1.7 equals 14. Between negative 1.7 and 9.25, the larger the pKb, the weaker the base. That means this is the weaker base. Just like we predicted that if this is the weaker acid, this will be the weaker base. Right? Down here, go ahead and predict which side the equilibrium lies, towards the reactants or towards the products. So here, can everybody hear me?
Yes.
Yes. Okay. So Carolina, that might be something on your side, on your um.
I can hear you also.
Okay. All right. So I was quiet because I had asked this question here. Which side will the equilibrium lie? Left, which is the reactant side, or right for the product side? And I got a couple of answers, I believe, and they gave me the correct answers. It's the product side. Okay. Why is the product side?
Because you said the larger, the weaker.
The larger the pK, the weaker the acid. So here, this is the weaker acid. It's very hard to write with a head. And this is the stronger acid. Now remember, pKa values are always given for acids. There are no pKb values for acids. Okay. This is stronger and this is weaker. My last question. The other two compounds are going to be the base. What are their pKb values? What is the pKb value of this compound? First one, give me that. And then give me the pKb value of the other compound. So what is the pKb of this compound? The first one on the left. That is incorrect, Hannah. This compound here called acetalide. What you should look for is what is the conjugate acid base pair to which it belongs. This compound here on the left is paired up with which one? On the right. It's paired up with this one. How do I know it's paired up with that one? We are talking about the one that loses a proton or donates a proton to give you the other one. So we have this compound donating the proton to give you this compound. Similarly, we have this compound here, water, donating a proton to give you hydroxide. So they are a pair. Then you apply that equation that pKa plus pKb equals what? 14. I heard 14, but is 14 correct? Oh, I think you're answering this part, yeah. Okay, yeah, that is equal to 14. Okay, so coming back to this part, what is the pKb of this compound? And you answered it correctly, Hannah. It's negative 11. Because negative 11 goes here and positive 25 goes here. 25 minus 11 gives you 14. Similarly, what is the pKb of this compound? Hydroxide. Something you already had found right here for this one. Anybody? What's the pKb of hydroxide? Right, negative 1.7. And everybody should be answering on the chat. Now, which one between the two pKb values, which is smaller? Negative 11 or negative 1.7 is clear. Negative 11 is smaller, making it the stronger base. So you notice how this base is weaker base and weaker acid. So which side the equilibrium lies then? It lies in the forward direction. Okay. Lies in the forward direction. And the reverse direction would be a very small arrow on the left. Okay. Now, this is basically the most important part of your study from this chapter. The rest of it is seeing acids and bases and identifying what makes an acid a strong acid and what makes it a weak acid. All right, let's look at uh, what makes a strong acid and what makes a weak acid. So there are going to be 5 factors. Actually, there will be 6 factors we are going to look at, which makes an acid a strong acid. And those factors are, we'll look at all of them today. Number 1, where do we start here? Okay. Electronegativity, right? Electronegativity is going to play a huge part in making one acid a stronger acid. Now, it's one thing that I give you the pK values and you figure out which side the equilibrium lies. But it's a totally different thing if you are not given the pK values, but you have to make an educated guess that such and such acid would be a stronger acid than the other one because of the pK values there. I mean, because of the electronegativity values. Let's look at an example. All right, here we have 1, 2, 3, 4, 4 different reactions. They are all acid-base reactions, right? Have a look here. This compound with water. Now, what's the difference between all of these compounds? Notice one is they are all acid-base reactions, Bronsted acid-base reactions. First of all, always be aware of what a Bronsted acid-base reaction looks like. You have a proton here shown in blue that is being donated to H2O to turn it into H3O plus. So this compound is the acid, this is the base. And down here on the other side, on the product side, this is the base and this is the acid. Okay, they are all very similar reactions because water is one of the reactants. Now, what's the difference between this compound, the acid, versus this acid, versus this one and this one? The idea is that we are going from carbon, and carbon will need 3 methyl groups. Okay, because carbon makes 4 bonds. One of them is a hydrogen, the other 3 are the methyl groups. Then we go to nitrogen. Nitrogen makes 3 bonds. So it has 2 methyl groups and 1 hydrogen. Then we have oxygen. Oxygen makes only 2 bonds. So it only has 1 methyl group. And then lastly, fluorine. Fluorine only makes 1 bond. So there are 0 methyl groups. There's just hydrogen. So all these 4 compounds are acting as an acid. And we are trying to figure out why there is a trend. Here is what we notice. The pKa of the last one, HF, is 3.2. The pKa of this one, second to the last, methanol, is 15.5. This compound second one here called dimethylamine. The pK is 40. And finally, this compound, this one is basically, it's called 2,2-dimethyl or simply called common name wise, we'll learn how to name it. It's called tertiary butane, third butane, T-butane sometimes. That's a pK of 50. So according to this, the strongest acid is the last one. Second strongest acid is the second to the last one, followed by the second one, and the first one is the least strongest acid, or the weakest acid. Now, all of these are, by the way, very weak acids. Anytime the pKa is, we already know HF is classified as a weak acid. pKa of 1 or smaller are usually strong acids. So this is a weak acid, right? And these are even weaker. In reality, these are so weak that they will not act as acids, but these are their pKa values. So what is the reasoning behind why there is a trend here? Acidity, if you notice, based on electronegativity values, acidity is increasing this way from left to right. This being the weakest, carbon giving us the weakest acid, followed by nitrogen, followed by oxygen, followed by fluorine. And if you were to look at trends between the next row, silicon, phosphorus, sulfur, and chlorine, we will notice the same trend. Silicon-based compound being the weakest acid, followed by phosphorus compound, followed by sulfur-based compound, and then chlorine. So left to right, acidity is increasing. And here is the reasoning why. These are all equilibrium reactions. Once we have the acid compound lose the proton, we get the conjugate base. And I want you to memorize this deeply, deeply understand this, that when you get the conjugate base is what defines if you have a strong acid or a weak acid. If the conjugate base is very stable, then you have a strong acid. Meaning, if the conjugate base being very stable makes it unreactive. So if it is stable, it's unreactive. And if it is unreactive, then it does not want to combine with the conjugate acid to go back in the reverse direction. Right? Again, let me repeat this. If the conjugate base is very stable, then it's not going to be reactive. How would it have been reactive? It would combine with the conjugate acid and go in the reverse direction. That is what would make it a weak. This acid would be a weak acid if it cannot maintain the equilibrium in the forward direction. If it can maintain the equilibrium in the forward direction, that would only happen if you have a conjugate base that is very stable. Now, when we look at the conjugate bases here, fluoride, methoxide, dimethyl nitride, and tert, this would be tertiary butane, so tert butanide ion. These are the four. Of all of this, the stability of the conjugate base depends on the ability to hold the electrons, the excess negative charge. So based on the electronegativity values, we know that fluorine is able to hold the negative charge the best, followed by oxygen, followed by nitrogen, followed by carbon, right? So fluorine is going to be the most stable. It can hold that negative charge, that excess negative charge, due to its high electronegativity. Right? Then it's the oxygen, then it's the nitrogen, then it's the carbon. So you want to do this test if you are given structures that are very similar. Only difference between them is the electronegativity values. Okay. So left to right, what determines the acidity of a compound? It's the electronegativity of the electronegative atom, which holds the negative charge. That is correct. The more electronegative the atom, the more acidic. But I want to clarify one thing. When I talk about electronegativity, we are talking about left to right. Okay, going from left to right. Now, if we were go from top to bottom, then another trend is in effect. It's not the electronegativity values, but it's the size trend, which we are going to get to next. So only when we are comparing two compounds in a given period, any two compounds in a period, such as comparing an acid made with boron versus oxygen. To think of, for example, boron makes BH3. BH3 is the compound that boron makes. Let's write it down here. BH3. What kind of a compound does carbon make? Carbon makes, now if I just add the hydrogen, CH4, methane. If I was to simply ask you, without giving you pKa values, which of this, if they acted as acids, which normally they do not, but acting as an acid means what? Just to donate a proton. And while they do not prefer to donate a proton, under certain circumstances, we can force them to donate a proton. So if they were to donate a proton, which one would be a stronger acid? Borane, this is called borane, BH3, or methane, CH4. Which of these two would be a stronger acid based on what we just talked? You tell me. Anybody? Is borane stronger than methane or methane stronger than borane? The answer is methane is stronger. Methane would be the stronger acid. Why? Because as we learned, acidity increases from left to right on the periodic table on a period like this.
So
So
basically,
carbon is on the right of boron, correct? Boron. So the acid, that carbon CH4 would be a stronger acid than BH3. All right. You can apply the same logic to silicon, silane, CiH4, and pH3. Okay, you can apply the same logic between any two compounds, such as HCl versus H2S. From left to right, it will be the one on the right that will be the stronger acid. Right. So now let's look at the other trend, not the electronegativity trend, but the size trend. Let's see. When it comes to the size of the atom, we have an example here. We are looking at, in this example, we are looking at this last vertical column. The size of the atom determines the trend vertically, okay, while the electronegativity determines the trend horizontally. Right? So here we have HF versus HCl versus HBr versus HI. HF is the acid made with fluorine. HCl is the acid made with fluorine. HBr obviously with bromine, and the last one with this one. What is the trend here? Look at the pKa values. The first compound has a pKa HF of that we are starting at the bottom where we are writing the pKs. We are starting with this one, HI, because that is the strongest acid. Hydroiodic acid has a pK of -10. That's HI. Then this one, second to the last, HBr, hydrobromic acid, has a pK of -9. Hydrochloric acid has a pK of -7, and hydrofluoric acid has a pK of -3.2. So acidity wise, the pKa's are increasing from top to bottom, which means the acidity is highest going down. Earlier we saw that electronegativity wise, the trend was this way, right? In terms of acidity. Now, size wise, the trend is from top to bottom. So the same logic we applied earlier for electronegativity also applies again. You will see it apply again and again. It's the stability of the conjugate base. So here also we are comparing the stability of fluoride versus chloride versus bromide versus iodide. However, the stability here is not due to electronegativity, but size. Okay. Size of iodide is the largest. Iodine is the largest atom. Iodide is also the largest ion, followed by bromide, followed by chloride, followed by fluoride. So why exactly is size the determining factor here? Because when you go down a group like this, the size blows up a lot because we now have a new shell. This is your n equals to 2 shell to n equals to 3 shell to n equals to 4 to n equals to 5. So the size of iodide is more than 5 times the size of fluoride if you are actually to look at this actual size of the atoms and ions. And the greater the size, the better the ability to neutralize the negative charge. The negative charge will be spread on a much larger volume. So it is not so strongly dense in one small area such that it would try to react and neutralize itself. The iodide is better able to handle that negative charge because it is more diffuse. It's spread out in a larger volume compared to fluoride. That is the logic why hydroiodic acid is the strongest acid. Iodide is the most stable ion of all of this, followed by bromide ion, followed by chloride, followed by fluoride. And this logic works with other compounds which you normally do not classify as acids. For example, take this column here. If I was to ask you, ammonia, NH3, was an acid, although we classify it usually as a base, it can act as an acid. It will act as an acid to donate a proton turning into NH2 minus called amide. Then pH 3 underneath it. And finally ASH3. Of these three, if you are asked which one is the strongest acid, what would you answer? Remember, electronegativity is not what determines the acid strength in a group or column in a group, but it's the size. And we know which is the largest atom. So which is the strongest acid here? That is correct. Many of you answered ESH3. That is the strongest acid. All right. Followed by pH3, followed by ammonia. Now the exact pKa values, you have to determine them experimentally. I'm sure they are published by now in textbooks, but we won't be able to find that out without doing an experimentation. So have a look here. We got a bunch of compounds. All the ones given here are being classified as acids. So we already know from left to right, acidity increases because of electronegativity, right? So HF's acidity, pK value versus water versus ammonia versus methane. Also look at these two. The one on the right is always more acidic than the one on the left. But then also look at the column from top to bottom. Water versus hydrogen sulfide versus hydrogen selenide versus hydrogen telluride. Okay, so you can see how H2TE, hydrogen telluride, is more acidic than hydrogen selenide, which is more acidic than hydrogen sulfide, which is more acidic than water. And we already saw this trend as well. Now the other 3 or 4 smaller factors that determine the strength of an acid, they are a bit more structural dependent. They are not just based on they are not dependent on large trends on the periodic table, but they are dependent on the structure of the compound. The next trend is called inductive effect trend. Inductive effect has to do with polarization of a bond because of a highly electronegative atom. So it goes back to an electronegative atom, but not directly like we saw earlier. The negative charge is not on the electronegative atom in this situation, but the electronegative atom is nearby. So let's show an example here. Okay, here, this is a nice example. So look at these acids. We talked on Monday how whenever you have C double bond O, OH, that's an acid. In organic chemistry, those are all the acids we talk about. Now, look at the first compound, which is 1, 2, 3, 4 carbon compound called butanoic acid. When it acts as an acid, it loses the H plus, it donates the H plus, giving you this compound here down here called butanoate ion. Now, this compound versus the next one, the only difference between these two is that there is a chlorine here. Chlorine is an electronegative atom, a rather strong electronegative atom with an electronegativity of 3.0. It's how far is it from the carbon on which we have the C double bond OOH? That's this carbon down here. So here, so from here it's 1, 2, 3, and 4th carbon. It's located on the 4th carbon. But look at the acidity, I mean the pK difference of these first two compounds. The first compound had a pK of 4.83. The second compound has a pK of 4.52. What does that mean? The one with smaller pK is the stronger acid, right? So having a chlorine is making this compound slightly stronger. What happens if this chlorine was moved closer? Instead of being on the 4th carbon, what if it was on the 3rd carbon? Now the pK is dropping even further, meaning it's becoming even a stronger acid. And moving it one more closer right here, the closest it can be to the 2nd carbon from this carbon. Now the pKa is much lower, 2.86. So what do we attribute this to? It's not directly the electronegativity factor, because electronegativity factor requires there to be a negative charge on the electronegative atom. Then it would be all about the electronegative atom or electronegativity. This time it's called inductive effect. Inductive effect is when you have an electronegative atom or some electronegative group for that matter. It will later on look at large groups which can bear negative charge. This is just an electronegative atom like chlorine or fluorine which can bear negative charge. When you have one of those in the structure, whenever we get a negatively charged conjugate base, and it always comes down to the negatively charged conjugate base on the other side, that negative charge can be pulled by the sigma bonds that are there between these groups towards that more electronegative atom. So here we don't have an electronegative atom except oxygen, which all of them have anyways. But here we have a chlorine. It can pull some of this negative density towards itself to stabilize this part, the oxygen with a negative charge. Here it can pull with a more force because it's closer. And here it can pull with even more force because it's even closer, the closest. So this is known as the inductive effect of either an electronegative atom or an electronegative group, where the negative charge is pulled towards it and thereby stabilizing the location where actually acidity or basicity is determined. Let's look at more example here. So here we got 4 compounds. Now notice here, this is the part which might confuse some of you, but look at these 4 compounds. What are they? They are all acids with one difference. The first one has iodine as the halogen atom here on the 2nd carbon here. Here we have bromine on the 2nd carbon. Here we have chlorine, and here we have fluorine on the 2nd carbons. Which is the strongest acid of these 4? The last one, the one with fluorine. So earlier, the reason I said that you might get confused is if you are not paying attention. And earlier, we were looking at the trend based on size, right? Size trend here. And we know that HI is the strongest acid and HF is the weakest acid because the conjugate base was just the iodide or the bromide, chloride, fluoride, and we are looking at their sizes. Now here, this compound, this last compound, this compound would be called 2 carbon, so it's a 2-fluoroethanoic acid versus 2-chloroethanoic acid, 2-bromoethanoic acid, and 2-iodoethanoic acid. Again, the names do not matter. But this last compound is the strongest acid, the one with fluorine, while this one, the one with iodine, is the weakest one. Why? Not because of size, and do not even attribute it directly to the electronegativity. Remember, it's the inductive effect because of the presence of an electronegative group or an atom. Fluorine is the most electronegative of these four. Iodine is the least electronegative. This is why you expect this compound, the last compound, 2-fluoroethanoic acid, to be the strongest acid. Furthermore, look at the trend on the bottom. Now we are looking at the same electronegative atom being added over and over. The first one, we don't have any electronegative atom beyond the normal structure of ethanoic acid. Then we have 1 chlorine added on the second carbon. Then we are adding 2 chlorines on that second carbon. And then we are adding 3 chlorines. Look at the acidity of this last compound. It's fairly acidic. Actually, it's one of the more acidic compounds. We have modified a simple organic structure to convert it into a very, very acidic compound. So it has a pK of 0.7. Okay. What is the reason? Because now we have 3 chlorines causing that inductive effect versus 2 chlorines versus just 1 chlorine and no chlorine here. Right? So inductive effect is also fairly easy to determine as long as we are comparing similar structures. Apple to apple comparison. Okay, I cannot simply take this compound here and compare it with, let's see. Well, I could not take this compound here, the 2-fluoroethanoic acid, and compare it to 2,2-dichloroethanoic acid, because now not only are the two atoms different, but between the two atoms, fluorine is the more electronegative one. However, we have 2 chlorines, so which one will be more acidic? That's hard to determine. Now, obviously, here we see the pKa values, so we know which is more acidic, but I would not ask you something like this in a homework or an exam, because there are 2 factors. One has 2 of the weaker kind of electronegative atom, and one has only 1 of the stronger electronegative atom. So as long as we compare apples to apples, then we can easily find which is going to be the stronger acid and which will be the weaker acid. Right? The nitro group, as I was telling you, that inductive effect does not necessarily require just a single highly electronegative atom, but there are groups which can serve as being highly inductive, meaning being able to pull electrons, induce the electrons towards themselves. So that one of the groups is a nitro group. Nitro is simply a nitrogen that's bonded to the main structure. Let's say it's usually depicted with R. And that nitro group is a very explosive group, by the way. If you know TNT, TNT explodes, right? TNT stands for trinitrotoluene. Toluene is like benzene that we had looked at in the past in the class, but it has 3 nitro groups on benzene basically and 1 methyl group. That's what TNT is. So it's a very explosive compound. Nitro groups are very unstable, and that's where explosions happen. Now, the nitrogen here has a positive charge on it, okay? And that is why whatever is on R, if the whole R structure was acidic with a negative charge somewhere after losing a proton, that negative charge will be pulled by towards the nitrogen because it has a positive charge and it wants to stabilize itself. And that is what would make the nitro group a highly a inductive group that's going to pull electrons. It's called an electron withdrawing group. There are other electron withdrawing groups, but we in our course are only going to look at the regular electronegative atoms and nitro group. But any group that has a positive charge on that atom that's directly bonded to the carbon, that group can serve as a electron withdrawing group. Here are some more examples of pK values. This is your bare ethanol. Ethanol acting as an acid, ridiculously high pK, put 15.9, so it's not a strong acid at all. But if we add a fluorine, it becomes a little stronger, still weak, but not that strong. But instead, if we added a nitro group makes it even stronger. Now, here, while I will ask you to compare the which is more electronegative atom on the periodic table and classify the acids as being strong or weak, I will not ask you to do the same with something like a nitro group. Nitro group can be a very strong acid making group or not so strong acid making group, but you know that it is an electron withdrawing group. So having it will always make the acid a bit stronger. All right, so we looked at three effects so far, right? Electronegativity effect, size effect, and inductive effect. The fourth effect, which we will look at, is solvation effect. Solvation means how good your compound can dissolve. If it can dissolve very well, it's going to definitely be a stronger acid, right? So here we have a compound called formic acid, okay? Formic acid is simply the compound shown down here. Now, when formic acid forms the conjugate base, it will lose this proton and you get formate ion, F-O-R-M-A-T-E, formate with a negative charge there. Now, this compound is if you dissolve it in water, water will form hydrogen bonds around that oxygen. Even though it's a very small conjugate base with a lot of negative charge here that is not being stabilized by the presence of an electronegative atom, all right? By elongating this chain and adding a chlorine or a fluorine, we would think that is what's needed to stabilize this. But it's a very small ion and water can easily come around it and form hydrogen bonds. Hydrogen bonds are basically delta H or delta plus on the hydrogen and delta minus on the oxygen that is getting stabilized by the delta plus on the hydrogens, right? So it is getting stabilized through hydrogen bonding. And if it is getting stabilized as a conjugate base, then that makes it non-reactive. And if it is non-reactive, that means the acid can move or propel the equilibrium towards the forward direction and keep it there, thereby raising the Ka and lowering the pK. Right. So here we are looking at these compounds. Look at all of these compounds. There is no what do you call it? The electronegative atom like fluorine or chlorine. There is no size effect either going from top to bottom. So there is no induction effects, there is no size effect, there is no electronegativity effects. What is going on here? We are basically simply elongating the chain. The first molecule only has one carbon. The second one has two carbon, and the second carbon here, this carbon needs hydrogens to have 4 bonds. Then we are adding 2 more carbons here, and then we are adding 1 more to that. So basically, we are just elongating the chain with more carbons. Why is the acidity decreasing? Why is the first compound the most acidic? It's the smallest compound, but don't go simply by the small size. Also realize that the part that we are adding as we go from left to right is all hydrophobic. These are just hydrogens and carbons. And those are non-polar groups, as we learned in our chapter 1. They are non-polar, and if they are non-polar, they don't like water. They are water-hating, hydrophobic. So they do not want to mix with water and easily open themselves up to being dissolved, or rather the correct word is solvated in a nice way. So if they are not solvated well, they are going to be reactive. And if they are reactive, they will try to move the equilibrium to the left, thereby raising the pKa value. Okay? The more reactive they are, the higher the pKa will become, because they will move the reaction to the left as conjugate bases. Okay, we are talking about the conjugate bases, the one with the minus charge with the hydrogen gone. While the first compound, once it's a minus charge, water can come around it very easily. Not so much here, not so much here, and the least here. Right? So solvation effect, that can depend on the structure of the compound you are looking at. And if it is a hydrophobic chain we are lengthening, then it will make it a weaker acid, because it will not dissolve well in a polar solvent like water. Here we have formic acid again. And basically, we are looking at what we just were looking at earlier. But now on the bottom, we can see this compound, formic acid, versus this last compound, which is 2,2-dimethyl propanoic acid. So formic acid allows water to come around it to form hydrogen bonds. Notice how many hydrogen bonds we can get: 1, 2, 3, and 4. While here, all of these groups are hydrophobic. They refuse to interact with water. And so water has to simply come in the forward in this area where you have this O minus, and we are able to get 2 hydrogen bonds instead of 4. So this compound is not as stabilized as formic acid. 2,2-dimethyl propanoic acid is not as stable in the negatively charged conjugate base form, which is called 2,2-dimethyl propanoate. That is not as stable as formate here. All right, the next effect, we got a couple of more effects to look at. This is the delocalization of charge, which is actually a long way of simply saying resonance effect. Resonance. So this is an effect. This is actually my favorite effect, personally speaking, if there could be any favorites or non-favorites here, but this is the one that I really like to study. So look at this too: methanol compound, methanol, the one we worked with in the lab, and acetic acid. Now, what's the difference between methanol and acetic acid? Here is, if we draw their structures, let me, okay, let me show the structure of methanol. It's CH3 group, as we all know. I'm not gonna draw anything novel. It's just what we know: CH3 followed by OH. Versus acetic acid now. Acetic acid also starts with a CH3. But then we are going to interject this group, carbonyl group, C double bond O. And then have OH. That's acetic acid. So there is a way to compare them, compare and contrast them. Simply, acetic acid has this carbonyl group between the CH3 and the OH, while methanol does not have that carbonyl group. All right. Look at the pKa difference between the two. pKa of methanol is 15.5, while pKa of acetic acid is 4.74. Clearly, acetic acid is much stronger. a billion times stronger. Each pKa value is a factor of 10. So a pKa value of difference of 2, 5 versus 7 would be 100 times stronger. 5 pKa of 5 will be 100 times stronger than pKa of 7. So here is close to a billion, 10 to the 9, if not 10 to the 11, a trillion maybe. But acetic acid is clearly a stronger acid. There is no resonance, there is no electronegativity effect. There is no electronegative atom. There is no size effect from top to bottom. They are all carbons and hydrogens and one oxygen or two. There is no inductive effect. We don't have an electronegative atom or a group like that nearby. And also there is no solvation effect. They are both fairly small. They are both about the same size. So what exactly is the reasoning behind why the second compound is a stronger compound acidity-wise than the first one? And that has to do with resonance. Let me clear the screen here. So we can now look at just these two on the right. So resonance stabilization of the conjugate base. Again, it all comes down to conjugate base. The conjugate base acetate here has resonance. As you see here, the C double bond O and here C single bond O can resonate here in this structure. The double bonds alternate. The double and single bonds alternate between these two oxygens. But there is no resonance possibility with the ion from methanol, methoxide. Okay, while acetate has the resonance stabilization, methoxide does not. So what exactly does resonance do? Well, it stabilizes the compound. The two resonance structures show that the negative charge is not local just to one oxygen, but is spread equally between those two oxygens. Okay, in one resonance structure is on this oxygen and the other resonance structure is on this oxygen. And both are equally contributing structures. They are both equally major. So the charge is being spread 50-50 on each. Here, all the charge is on the single oxygen. What does that mean? It's highly reactive. And highly reactive means it goes back to what it was. While here, it's less reactive. So smaller chance of going back to what it was. That's why the pKa is smaller here than here. Okay, delocalization of charge or resonance effect. You need to be able to draw resonance structures in this case to be able to see the effects. That is why this is my favorite, because you are going back to resonance structures. So here we are looking at these two structures. One structure up here is called, this is phenol, okay, phenol. And here we have acetic acid, but phenol has way more resonance structures than acetic acid. Okay. However, do not just assume that if one structure has more resonance structures, one compound has more resonance structures, then that means it will be more stable. First of all, this is not comparing apples to apples, right? These are two different structures. Try to compare only apples to apples, not like different structures and counting the number of resonance forms they have. But there is a reasoning here why the second structure is more stable. Because in the first structure, this negative charge is being spread on carbons. Remember, when we are drawing resonance structures, we learned that we want to put the negative charge on the more electronegative atom, like oxygens or nitrogens or fluorines, not on any atom. And carbons are not that electronegative. They have an electronegativity of 2.5. They don't want a negative charge. So while there are these four resonance structures, they are really not that good at contributing to the overall structure. Versus here, even though there are just two, but in each of them, the negative charge is spread on an oxygen. So that's why this, despite having just two structures, has a smaller pK than this structure of phenol with 9.92 pK. The last one I want to talk about, and that's where we will end this lecture. On this chapter is mostly done, but we want to spend about 15 minutes afterwards on Monday looking at base strengths. We looked at acid strengths, which is going to be like 80% of your questions, but we will have some questions in the exam, in the homework on comparing two different bases. The same logic applies, okay, with bases as well. It's just that we look at it from a different perspective, which we'll talk about on Monday. But here, the last aspect of the factors is hybridization. And hybridization is also one of the ones where you need to put your brain into it and not just look at the periodic table here. Look at this for three compounds rather. The first one here, second, third, each one is separate from the other in some unique way. It has nothing to do with electronegativity or size of an atom or inductive effects or solvation effects or resonance. There are no such effects. What if you draw their Lewis structures? Here they are Lewis structures of the conjugate base. You will notice that this carbon here is sp3 hybridized with 4 electron groups. This carbon is sp2 hybridized with 3 electron groups, and this carbon right here down, the last one, is sp hybridized with 2 electron groups. So what does it mean to have sp3 hybridization? It means there is 25% S and 75% P. Remember that, because it's made up of 1 S and 3 P's. That means we are taking 25% of the S character and the other 75% is the P character. When it's made up of sp2, that means there is 1 S and 2 P's, a total of three different orbitals, S and 2 P's. And so 33% is S and 66%, or to be more precise, 33.3% is S and 66.7% is P. And finally, if there is just an S and a P, then both are 50-50 combined together. The greater the S character, the stronger the acid. So 50% S will give you a stronger acid than 33.3% S versus 25% S character. Why is that? Because the electrons in the S orbital are held more closer together. They are tightly held. S orbital is closer to the nucleus than the P orbital, right? So if they are in the S orbital, then they are less reactive. If they are held more tightly, they are less available for reaction, thereby becoming more stable. Here you can see that in the diagram form, how this orbital is smaller versus this one, and this is the largest. The farther away from the nucleus, the more available they are for bonding and reacting. So S character matters if all the other factors are not there. And all the examples you will be asked or given, they will only be related to one or the other of this, all the factors. Either it's going to be related to electronegativity or size or inductive effects or solvation effects or resonance effects or hybridization effects. From those 6, you will have to go through the list of all those 6 and determine which one applies in that particular case, and then determine which will be the strongest acid and which will be the weakest acid of the compounds. Okay. Here, there is one last we are going, this is hybridization again. So here we have sp hybridization, sp2 hybridization, sorry, 1, 2, yeah, sp2 hybridization, sp hybridization, and sp3 hybridization. This is sp2 hybridization. So here we have this ammonia-based compound, which is more electronegative than the others, more electronegative than carbon. So here we have sp2 versus, where is the other sp2? Here. This is also sp2. These are both sp2 compounds, the middle two compounds. And sp2 versus sp2, here what are we exactly comparing now? We are not comparing hybridization then, because they are both sp2. So you can't really compare. Then you are looking at the presence of the electronegative atom, nitrogen. That's why the pK is 38 versus 44 here, right? So it is not the hybridization between these two, but it's the electronegativity of nitrogen. But the other 3, number 1, number 2, and number 4, can be compared simply based on their hybridization. All right, so Monday we will talk about base strength. This is where we will end it. And so it is 10:45 for the lab. Let's meet at 12 o'clock. How about that? In the lab room. Is that good? I'm giving you a little bit longer to get ready. Yeah, noon, 12 p.m. Yes. Okay, so I will see you there at 12. And by Monday, everything should be fine. We have been told that the room will be ready, but usually there are delays with everything in life. So I don't know if it will actually be ready, but I'll let you know during the weekend. And when we meet, I will talk more about homework one, because the textbook rep keeps on insisting that it works. They even logged in as a student and showed me that it works. So I want to see from your end what is happening later on today, and then we can figure out what to do. And homework two, I have already opened up for you to work on. Okay. All right. I will see you at 12 and we'll talk more at 12. All right.